First, the homework problem from last time. Thank you. Thank you, George. First, the homework problem. Let's have a look at it. Has anybody done anything about it at all? No? Was it too hard? Or was it just not enough time? Too many other things to do, I suppose. Okay. Right, so how does this work? Okay. You're trying to solve shortest paths using integer programming. Okay, that's the idea of this. And in this particular case, what you want is, if you want to chat, can you please go? And just go and chat somewhere else. Sounds like a good idea. Thank you. So what we want to have is, it kind of says in the question, is that you should have a binary, so that's a 0, 1 variable, decision variable for each of the arcs of this graph. So that would mean that the decision variables would be x1 for SA, and then you have SB, and then you have SC, and so on. Okay, and I'm not going to list them all, but you kind of get the idea that for every pair of vertices where there's an arrow going from the left to the right, you put a decision variable from S to C, from C to T, and so on. Okay. So these are the decision variables. Now, you want to kind of, what you're thinking is, in the optimal solution, you want this decision variable to be 1 if that particular arc is used on the shortest path. Again, 0 otherwise. So this will be the interpretation of this. And so with this in mind, you want the objective, you want to minimize the length of that path, right? So what you want to do is you minimize, well, I'm not going to, what I'm going to do is say that does it show yet? The length of any arc from X to Y be, let's say, L, X, Y, okay? So for example, you would have LSA is 4, and LAB is 2, and so on. And then what you want to minimize is, maybe X is not a good, well, it comes up there. Well, that's okay. So you look at all the arcs that are 1, and you add their lengths together. And for the variables where it's 0, you're not adding anything, and that's going to give you, if you E is the set of all arcs, then this sum is going to give you the total length of the shortest path. If you have that they're exactly 1 on the shortest path and 0 elsewhere. Okay. But somehow you want to make sure that the constraints that you put there make the ones to be the shortest path, or a path anyway. And the shortest one is then going to be given by the minimization, but you want all these things to somehow denote a path from S to T. Right? So firstly, what you want is first constraint, well, it does say here that one of the constraints makes sure that exactly 1 arc from S is in the shortest path. So you want exactly 1 arc from S. Well, how do you get it? Well, you look at what are the arcs leaving S. It's SA, SB, and SC. So you want X, SA, SB, SC to add to 1. And that will mean, if you make them binary, it will mean that exactly one of them is going to be 1. So exactly one of them is going to be used on the path. Okay? And you also want exactly one arc into T. And the arcs going into T are AT, BT, CT. So you want AT plus XBT plus XCT equal to 1. And again, this makes exactly one of them to be 1, and that makes exactly one of them to the arcs to be used in the path. Right? And then for the remaining vertices, so for A, B, and C in this case, you want that if you come there, then you won't have to leave. And if you don't come there, then you can't leave. Okay, so the number of arcs that you've selected coming into A, it has to be exactly the same as the number you've selected leaving A. So in this case, coming into A is just from S, and leaving is to B and to T. So for vertex A, you want that XSA plus is equal to XAB plus XAT. Well, what does that mean? That means that if you're coming into A from S, so this is going to be 1, then you have to use exactly one of them to leave A on your path. Okay, and if you're not coming there at all, then you can't use any of them. And then you have a similar thing for B. So for B, you have 3 things coming in from S, A, and C. SB, C, sorry, ASB, no, what am I doing? CB and AB. So all the things that go into B. And all the things that on the other side, all the things that leave B, and there's only one. And similarly for vertex C, well, it's the same thing, kind of. So the only thing that goes into C is SC, I think. And the things that the arcs that leave C are CB and CT. And then you want all of them to be 0, 1. That's a slightly weird notation, but that means for all decision variables, we want them to be 0, 1. Kind of a sloppy notation, but you get what I mean. I'm not sure you'd be okay to get away with this in the exam. Probably, yes. So that's the formulation. Any questions about the formulation at all? No? Making sense? So then if you solve this using any method you want, I think this comes out as the shortest path. So you would have XSC is 1, XCB is 1, and XBT is 1, and all the other x's are 0. Yeah, that's everything. Now, if you have solved it, which you said, mark it. Right, so the plan for the rest of today's lesson is we'll have another look at the branch and bound algorithm, kind of summarize what we did last week, and then after that, we'll look at some formulations. So how do you take problems that look like a real life problem and produce basically this kind of exercise. Some easier ones. This one was a bit challenging, quite interesting, I think. Right. So this was the example we were looking at last week. And yeah, and the way we solved it was we used these things called the ILP relaxations. So an ILP relaxation of an integer problem like this is a linear programming problem, as ILP would suggest, in which you forget that these variables have to be integer, and you just want them to be non-negative. And so if you solve that problem, we saw it last week, and x1, x2 just have to be non-negative, but not necessarily integer. The solution you're getting is going to be this one. And they're called relaxation because they're more, so kind of the term for being more relaxed, so there are fewer constraints. Something has fewer constraints, subset of the constraints, and it's called a relaxation. And but what we have here is kind of bound. So because if we allow these values to be fractional, the maximum we can get is 59.7. That means that if we add the constraint that they have to be integers, the solution certainly can't be better. It can't be more than 59/7, because 59/7 was less than 9. The solution of the integer problem, because we know the objective is going to be an integer, can't be more than 8. Okay, and that's the idea of the bound bit of that thing, and the idea of the branch, as we saw, was when you solve the problem like this, you get the optimal solution of the relaxation. If these things are all integers, then you're happy because you found your optimal solution. But if they're not, then you pick one that has a fractional value, and this is something between 2 and 3. So then you create 2 subproblems in which one of them is less than or equal to 2, and the other one is greater than or equal to 3, because no integer can be more than 2 and less than 3. They have to be either less than or equal to 2 or greater than or equal to 3. No integers between them. So like this, you've covered all the integer solutions, but at the same time, what you won't get again is x1, which has a fractional value between 2 and 3. So the optimal solutions for the ILP relaxations of these subproblems where you add a component constraint are going to be different to this one. You're kind of making progress. You're trying to make feasible regions smaller with every step. Here you've made it so small that there are actually no feasible solutions. Okay. And on the other side, we get something that is less than 8, but no more than 8 of this. Or in can't be more than 8. And but again, it's not all integers. It's not all integers. We do the same trick. So one of them is x2 less than or equal to 0, that's 0, and the other one is greater than or equal to 1. When you solve these relaxations, you see one of them gives you an integer solution, so you stop branching here. You also stop branching here because it's infeasible, so there's nothing more to solve. And the non-trivial one, really, where you stop branching is you don't continue here. The reason for that is because no matter what solutions you find out there, they're not going to be better than 6 in their objective. You already have an integer solution that's an effective value of 7. certainly not going to be using the branching. That's what stop branching. So that's how the algorithm works. Now, written out, it's this. So what you're doing is you always keep some sort of a list of, so this is the list of problems that you haven't solved yet. And in the beginning is just the original problem, the whole problem that you got. But then you keep adding as you branch. So whenever you do the branching, you create 2 new subproblems and you add them on the list. And then you keep a certain bound, which in the beginning is minus infinity. So this is the objective value of the best integer solution found so far. And this thing called the incumbent is you just remember the best integer solution found so far. Okay, and then in the end, so you always keep track of what the best is you found ever, and then in the end, when you finish, the best you found so far is the best ever, and that's the optimal solution. This is how that works. And then how do you keep working on it? So when you look at your list and there's something on the list, you pick a problem on the list, you solve its LP relaxation. If you find it's infeasible, then there's nothing more to do. So you stop branching. Prune means stop branching. And you've already solved it, so you remove it from the list. If it is feasible, but you find something that's worse than the current best integer solution you know, then you stop branching because it's never going to be optimal in that particular branch. So that was the case of the leftmost branch we had. Now, if you find an integer solution, then what you need to do is you compare it to the best you know so far. Okay, so if you found a better one than the one you know to date, then that gives you the new best. So this means that there is a new best integer solution found so far. If not, then you don't update, but still you stop branching because you've already found an optimal solution in that branch. So you by optimality, sometimes you say by integrality, you found something that's integer. And if you don't stop branching, if you don't prune, you create 2 subproblems and add them to the list. And once you've pruned everywhere, so you're not branching anywhere, this loop ends. And then you look at whether you've ever found any integer solution. If not, then the problem has no integer solutions. And if you have, then you return what the solution and you found the optimal solution. Okay, that's the algorithm again, a bit more formally. Any questions about that? No? Is it clear how it works? Is it too simple and I'm making too much fuss about it? Well, we'll see. There are some questions about how do you choose which branch you go down first, so or next, and that's not clear. So there is no good rule for that, because it's a hard problem computationally. If there was a guaranteed good way, I would tell you, but I can't because there isn't one. And When you get a solver something like Mosel or so, what it will typically try to do is go down a promising branch as deep as possible first, usually, and then it finds some integer solution. And once it's found some integer solution, that's good, because then it can start pruning by suboptimality. Before you've found any integer solution whatsoever, you can't do that, and so you would grow your tree a lot. So it's like a good idea. So it seems to be a good idea. So you branch at the top, then you branch here, then you keep going down. First, okay. Now here you found something that's integer. So once you have this bound, some integer solution that may be this one you don't have to do anything about because it's because you know it's suboptimal, and this one you don't have to do anything about because it's suboptimal, and so on. So maybe then you start branching here. Okay, this one is suboptimal. But before you have an integer solution, you can't branch, or you can't prune by suboptimality. So it's always good to find one quickly. And then afterwards, perhaps you choose among the unsolved problems the one. Well, among the problems, you choose the one where you kind of are getting the best value of the objective for the parent, or something like that. And that's, because like that, we're trying to solution as quickly as possible, but there's no guaranteed way. So that's this question, and the second question is what subproblems you create, and that's described here. Yeah, it's a lot of text. I don't want to read that. Well, you know what we're doing. So, for example, so x1 is 27.3, x2 is 15.4, and x3 is 10.1. So you do one of three things. You don't do all of them at once. So what you have is this problem, and you're trying to do the two branches. You don't branch on each of those variables. You just have to pick one of them. And so this was here. So one option is you could go for x1 is no more than 27, and x1 is greater than or equal to 28. Okay, so that's one possibility. Or you could do x2 is no more than 15, and x2 is greater than or equal to 16. Or you could do x3 is no more than 10, and x3 is greater than or equal to 11. But not all three, or not two of them. And which one to pick? There's kind of a rule, maybe not, again, not guaranteed to work always, but you choose the one where fractional part is as close to 1/2 as possible. So in this case, you choose this one, that's close to being in the middle, and it's close to 10. So there's no guarantee, of course, that's the best one, but much of the time it works better than not following it. So choose the variable whose fractional part is closest to 1/2. Kind of like the most fractional one. Okay, so this is what the computer will do normally, but we want to practice like we practice the simplex method, which the computer does normally. So for practicing, you've got a homework exercise. Just an example, randomly chosen example. And then you have another one in the coursework assignment. Maybe you can start with this one and you learn it, and then you can do the assignment. Because we'll check this one next. What you do is you follow the algorithm, but you have to have a way of solving the linear programs. Okay? So some people have already asked me how to solve these linear programs, and you can do whatever you want. So what you could do is do it in the simplex method in tables if you want, or you could do it using MATLAB, which also has a linear programming solver, but then you have to write everything in matrices. Or you could use the solver extension of Excel, or you can use Moz. So this homework problem suggested you should use a Mozel code, which is given there in the homework. It's not very complicated. It just says that you have 3 decision variables, you have 3 constraints, you have some objective. This get prop stat thing that just looks at whether the problem you found, well, you've tried to solve is feasible or not. If it's infeasible, then it's infeasible, and if it's not infeasible, then it's optimal, and if it's not optimal or infeasible, then something went wrong. Unless it's unbounded. Yeah. So that's if you don't want to write all these things, you can skip them, but then you have to check in somewhere in Mozel it gives you the answer whether you found a feasible solution or not. You have to be careful because sometimes it just prints the optimal solution, even though the problem is actually infeasible. So it's tricky. Okay, that's the homework. Any questions about branch and bound? So now let's have a look at this. You solved it? Now we're changing topic. Now instead of talking about how to solve ILP formulations with constraints and variables and an objective, we're going to our favorite topic of getting a problem that looks like a real life problem and writing those constraints and objectives that this is right. This is quite common. It's actually called a knapsack problem. Very often in the literature. Any decision variable?
If you refer to each item yeah. 8 items.
What do you want to call them? Okay. I going from 1 to 8. And you said you want them to be equal to 1, means take that item, and 0 means not take it. Yeah. Okay, I agree. What's the objective? Does it say? Greatest total value.
Maximize the sum of PI.
Like this? How does that depend on what you take and what you don't take? Yeah, that's better. The thing you don't take, their value is times by 0, so it doesn't count. The things you do take, their value is times by 1, so count. Simple. Simple. And what are the constraints? Well, total weight is not more than the maximum weight you can carry.
WI. Dummy. That's all.
Okay, I agree. Same principle going on here. Yeah, the W's are the things we take. I read it, and the W's are the things we don't take, or times by 0, so they don't count. Anything else? Just the usual stuff. What's the usual stuff? Non-negative constraints, but in this case, you want to make sure that they're actually binary, not just non-negative. So you want that each of them is either 0 or 1. If you want, because, yeah, we've talked about this before, but I'm just saying it to remind you that this is the same as saying that xi is between 0 and 1, including 0 and 1, and integer. It's the same thing as saying it's 0 or 1. What kind of justifies that we can use this, because that, strictly speaking, is not a linear inequality. But these are linear inequalities, and together with the integrality, which we're also allowed to use, we can then write that. Okay. That's simple. How much time is left? I'm getting a bit lazy. So Okay, so how would one solve that problem in Moser? Well, you have to say what the decision variables are. What are the decision variables? X1 to X8. So it's the best way, of course, you would put them into an array. So you would say X is an array 1 to 8 of MP var. And you want a profit or whatever. That's the usual thing. So you want some I in 1 to 8 of, oh, I didn't say what the W's were. So you also have to say that you have a W in an array. And P. So what you want is Pi times Xi. Okay. And the constraint is that the sum of Wi times Xi is no more than W. So somewhere here you would write W equal 20 kilos, for example. You weren't given any values in this case, but of course if you were solving it, you would have to know. And the thing that's new is that you would have to say this, that they're all binary variables. So what you do is when you get for all, and the word for this is that it's binary. Okay, with an underscore between is and binary. And that's the new bit. And then you just maximize profit. And that's it. So that's just a glimpse of what you would do if you wanted to solve it. If we had 10 minutes and I didn't want to start the other problem. That's something finished. So of course, you would have to add here as well what P's and W's are. Let's W. The values, initialize those arrays, otherwise you would just give them 0 because the things are all 0. Unless you tell it otherwise. But that's the simple thing. Any questions? Okay, then that's it for today. Hope to see you on Friday.